Next topic, components of simulation. So up to this we discuss about design block. So we have to design a circuit. So here once you design a circuit, it must be tested. The functionality of design block can be tested by using stimulus. So the block is called as stimulus block. Stimulus block, it does not require any additional language. So we can possible to implement using Verilog HD. The stimulus block is also called as test bench. It's very popular word with respect to Verilog HDL. So after this, in stimulus there are two styles of stimulus. The first one is, just observe the figure. Here we are to using a design block and also a stimulus block. Here the stimulus block is comes under top level block. So here stimulus block instantiate the design block. So here clock and reset are drive directly, and also here we check the queue and as well as display the results. Second style of description, you just observe the figure. In top level block, within the top level block, both design as well as stimulus. Here both the blocks, design and stimulus, both the blocks within the top level block. So here stimulus and design block both are instantiates in the top level block. D underscore clock and D underscore reset, it belongs to stimulus block, and also clock reset Q is belongs to a ripple carry counter. Here D clock and D underscore reset drives the design block, and also after drives the design block, the results in the form of D underscore Q and also display the result. I repeat. So first one, stimulus block is belongs to top level one. So here directly drives the stimulus block is directly drives the a design block. But here stimulus block, it's connected interface with respect to design block. So that is the difference between the first method as well as second method. So usually for the Verilog purpose, we have to consider one is first one. The first one is enough for a simple circuit. Simple circuits in the sense, so we have to consider full adder, off subtractor. So this one first style is enough. You go to a complex circuit, for example n bit adder, 10 bit adder, so that belongs to a second style. So this is the component of simulation. So once you test the both stimulus block and design block, so we have to take examples. So in the examples, first we write the design block, then we go to stimulus block. Example, we have to consider a example for both design block as well as stimulus block. So here let us take 4-bit ripple carry counter. So 4-bit ripple carry counter, there are 4 flip-flops required. So usually the selection of flip-flops is depends on the nature of which one is faster. So usually we are going to a T flip-flop. Why T flip-flop? Because it's faster than other flip-flop. When you apply the T is equal to 0, and that time there is no change. When you apply T is equal to 1, then it's continuously toggles. So it's very good suitable for 4-bit ripple carry counters. The counter, 1-bit counter required a 1 flip-flop. So there are 4-bit ripple counter, so there are 4 flip-flops is required. So they just connected all the 4 flip-flops, then it becomes an 4-bit ripple carry counter. So let us so this is a T flip-flop. So it acts as a 1-bit count. It acts as a 1-bit counter. So here we have to consider clock, reset, and Q, and as well as D. So here entire T flip-flop is designed by a D flip flop and then inverter. So we'll discuss later. It's an one bit counter. So T flip flop. So it named as T underscore FF. Then subname is T underscore FF not. It indicates first flip flop. So here we have to apply a negative clock pulse, negative edge triggering. So here just observe the bubble. So it indicates an inverters. Next we have to apply the reset, another input, then getting the Q naught. So here it acts as a 1 bit counter. You just connect it to what? Another one, then it becomes a 2 bit. So totally we have to connect a 4 T flip flop, then it becomes a 4 bit ripple carry counters. So next, after this, this is the block diagram for 4 bit ripple carry counter. So here first we have to apply the clock. So it's an asynchronous counter, because in synchronous counter we have to apply the clock simultaneously. So here for asynchronous counter we have to apply the clock for the first stage, then for second stage clock acts as a what? Previous output. Okay, so similarly here. So here the clock depends on the previous output. So that's why we called as it's an asynchronous counter. 4 bit ripple carry asynchronous counter. So first stage we have to apply the clock, then D is the input. So D it may be 0 or 1. It depends on the designer. So here Q is the output. Q is the output. Here the first stage of the ripple carry counter we call it as Q naught. So Q naught acts as a clock for the second stage. So similarly you are getting a Q1 here, then Q1 is the output for the second stage. Then we have to apply the clock for the next stage, that is third stage. So we are getting Q2, so Q of 2 a third stage output, then similarly Q of 3 is the last stage outputs. So this is the simple diagram for a 4 bit ripple carry counter. So here you observe carefully T underscore flip flop for all the flip flop. So we name it as T underscore not 1, 2 and 3. So we will discuss programming, why we write TFF 0, 1, 2, 3. So next, this belongs to a top level block. Okay, we already discussed a top down design methodology. So it comes under top down design methodology. So top level block is 4 bit ripple carry counter. It's the top level block. Again it's divided into sub blocks. So there are 4 sub blocks here. There are 4 flip flops. So again this can be done by using one more diagram. So T flip flop is designed by one more flip flop, that is we have to assume that is it's a D flip flop, then we have to apply the clock. So this is the a T flip flop diagram. So it consists of a D as well as one inverter. So combination of D flip flop and an inverter we called as a T flip flop. So here there are two inputs here, that is reset and clock, and output is Q. So we know the truth table for the D flip flop. When you applied the D is equal to 0, then clock and reset its appropriate value, then whatever input you applied, then getting the at the output. Write the equation Q is equal to D. So here whatever changes in the D, it's directly proportional to what? A Q. If it is D is equal to 0, then Q is equal to 0, then D is equal to 1, then Q is equal to 1. So this is the what a T flip flop using a D flip flop and the inverter. So here entire this block diagram we are using a top down design methodology. First we have to write the a 4-bit counter block diagram. Next we write the sub block. Here sub block is the a T flip flop. Once you design the T flip flop sub block, next we have to go to next leaf cells. So there are two leaf cells with respect to this one is a D flip flop, another one is T flip flop. So up to this one we have to write the design. So first we have to write the a design block. So design block is done, we have to write the internals of the design block. Internals we also called as coding part of the a design block. Once you completed the coding part of the design block, next move on to a stimulus block. Okay, so next first we consider we have to write the code or we have to write the module internals for the design block. First we consider a design block, we have to write the code. The Verilla code is always start with module. The module name, it's very important one. Name it as ripple underscore carry underscore counter. So we have to mention inputs and outputs here. So we know that what are all the inputs we already defined with respect to block diagram. Reset is the one input, then clock is the one more, then Q. So these are all the inputs for what? Ripple carry counter. It's not T flip flop and D flip flop. It's only for a ripple carry counter. So after this we have to declare inputs and outputs. So input here, input is reset and clock. The output is, so output is, it's an 4-bit counter. So obviously it's an 3 down to 0. It indicates a 4-bit Q. So it's nothing but a Q of 0, Q of 1, Q of 2 and Q of 3. So here in ripple carry counter, 4-bit ripple carry counter, so there are 4 instances. 4 instances we have to write here. The first instances, so here T flip flop, then TFF0. So TFF0 is the what? The first instances. So in first instances, what is the output? We already write in the block diagram, that is Q of 0 is the output. Next we have to declare the inputs. The inputs are reset and clock. This is the first instances. So next we have to write the second instances, TFF1 we name it. We already discussed in the block diagram. So the output, it changes to Q of 1. So reset is, there is no changes because we applied reset simultaneously for the RZ flip flop. So we have to apply the clock for the first stage only with respect to TFF0. For the second stage, so Q of 0, it acts as a clock for the second stage. So next we have to write the next one, that is third one, TFF2, output of the second stage, that is Q of 2, then there is no changes with respect to reset, then Q of 1, it acts as a clock for the TFF2. So next continuation, TFF, T underscore F, TFF. So here for the last stage, Q of 3 is the output of the last state, then comma, so reset is, there is no changes in with respect to reset, comma, so clock for the third last stage, so Q of 2. So after this, so we have to write all 4 instances, TFF0, TFF1, TFF2 and TFF3. So after you declare all the 4 instances, next end the program, that is end module. So this programming is called as gate level description, or we called as a structural level description. Again we discuss all those things in detail in later modules. Then after this, once you declare the all the 4 instances, we have to write the internals, or we have to write the code for T flip-flop, because this is the a 4-bit ripple carry counter. So we have to write the T flip-flop. So we know the name of the module, so it should be same. We have to write this name, okay, T underscore FF. So outputs and inputs, so the Q is the output, we already discussed with respect to block diagram. So Q is the output, then clock and reset is the input. So next, input, clock, then output, input, clock and reset, output, Q. Okay, it's only for T flip-flop. So next we have to write here for T flip-flop there are 2 instances. So what are the 2 instances? One is D flip-flop, another one is A inverter. So first we have to write the A instances of D flip-flop. You simply write DFF, then DFF0 you have to mention, then we know the output and input here. Okay, what is the output? Q is the output, then clock and reset is the input. Next we have to write inverter, okay, not, then name it as N1. So for inverter the output it's D, input is Q. Okay, don't forget, don't confuse here, because for not only D is the output, then Q is the input. For here the D flip-flop, Q is the output, then clock and reset is the input. So here D, so we are not declared D anywhere here. So here after output we have to declare a intermediate signal. So that intermediate signal we have to call as a wire with respect to Verilog module. So first instances it's D flip-flop. The second one is you directly define the a not one, because there are so many primitive gates are available with respect to Verilog module. It not is the one of the primitive gate. So once you declare the a 2 instances, next end the program, that is end module. Again the operation, the design block is not completed, because here we have to define the a T flip-flop only. Again we have to define the a D flip-flop. So not is already done with respect to a primitive gates. Next we have to consider a D flip-flop. So we have to write the a D flip-flop code. After completion of a module, that is a T flip-flop, next we have to consider these instances. So we have to write these instances here, that is we have to write module, name of the instances, that is D underscore FF. We have to declare inputs and outputs. So D, then clock, then reset, Q. So next we have to declare the inputs and outputs. Input D, then clock and reset is the input, then output Q. We have to write output in terms of register. Why? Because of here we have to write the only a D flip-flop operation. We are not write any other operation. Okay, D flip-flop is the the final leaf cells. So that's why in this program we have to write in terms of a behavioral description. So that's why output acts as a register here. So we discuss in detail again later modules what do you mean by behavioral description. Okay, but here the output acts as a register here, that is we write register Q. So once its declaration is completed, next move on to always is the one of the predefined word with respect to Verilog HDL, then always at always at pause it reset. When it is pause it's continuously changes. Or as well as we have to consider very important factor, negative clock. We already discussed, so we have to apply a negative clock. So that bubble indicates it's a negative clock. Once you declare the always operation, that is pause it reset and negative clock, next move on to we have to apply this data operation. So if reset, okay, it meaning is reset is equal to 1. We can write reset is equal to 1, or we simply write if reset. If reset is equal to 1 and that time Q is reset, that is Q is equal to 0. Else, there is a if operation, we have to write else. Else the condition is Q gets equals, or you simply write Q is equal to D. So it meaning, so when you apply the negative edge of the clock, then Q is equal to D. So whatever D is applied, it's directly proportional to Q. So after this, end the program using AND module. A deep flip-flop module internals using behavioral description. So once the design block is completed here, up to this step, a design block is completed. So we need to test the design block. So that can be done by a stimulus block. So next we have to write a Verilog code for the stimulus block. We check the output of the a 4-bit ripple carry counter. So next move on to stimulus block. Stimulus block is the second part of the continuation of the design block. So once the design block is completed, we must test the design block. So that can be done by using stimulus block. Here module, name of the module is stimulus. You can write any other name, stimulus. Then here register and wire we have to use here. So in stimulus block, register acts as a input, wire acts as a output. So it's applicable only for a stimulus block, or we called as test bench. So here register clock is the input of, then reset is the another input, then wire is a 3 down to 0 Q. So here we have to write this stimulus block for the 4-bit ripple carry counter. So after declaration of wire, this is very important step, ripple underscore carry underscore counter. The name should be similar with respect to a ripple carry counter design block programming. So here the name here same, ripple underscore carry underscore counter. Then here we have to declare the inputs and outputs. So Q is output for ripple carry counter, then clock and reset for input. So once this line we called as stimulus block instantiate the design block, that is ripple underscore carry underscore counter, we have to declare the inputs and outputs. So after this we have to apply the data, we have to apply the inputs and output for testing purpose. So for testing purpose, initial is the predefined word with respect to stimulus, then clock is equal to 0. It means the initially clock is equal to 0, then we are using always word. Why we using always word? Because of the clock should be toggle every time. So in programming we have to clearly mention the clock should be works with respect to edge only. So that's why we are using always word here. Always #5 clock is equal to not of clock. So this is the symbol of NOT gate. So why it is indicates here #5 nanoseconds? It means the clock is toggle every 5 nanoseconds. So that's why we write clock is equal to, so not of clock means it toggles every 5 nanoseconds. So once you mention the clock, next move on to reset, because here there are two inputs here. One is clock, another one is reset. Let us consider reset here. Begin, initial, again we consider begin, reset is equal to 1. So we declared in programming when reset is equal to 1, and that time the everything is 0, that is output is equal to 0. So first we reset the entire counter, next we move on to what? Reset is equal to 0. So after 15 nanoseconds, so it indicates as 15 indicates after 15 nanoseconds, so it becomes an 0. So here after 20 nanoseconds, then it becomes an 0. So up to 180 nanoseconds, or be after 180 nanoseconds, so it becomes an 1. So that's why here we have to write the a simulation operation. Okay, so here after a 180 nanosecond becomes an 1. It becomes an 1 in the sense again the counter is reset. So after 10 nanoseconds, so it becomes a logic 0, again the counter is works. So again after 20 nanoseconds, so it finishes. So I repeat this, reset is equal to 1. If that is initially reset is equal to 1, the counter is reset. Then after 15 nanoseconds, okay, after 15 nanoseconds, so it becomes an 0. So up to, you just add the nanoseconds here, 15, 5, 180, up to 200 nanoseconds, it becomes an what? A 1. So up to 200 nanoseconds, the counter is continuously work. So after 200 nanoseconds, again it becomes an 0. So it should be what? Reset the counter. So we need to stop the programming. So that can be done by a 20 nanoseconds, dollar symbol finish. So it indicates the counter is end. So the initial, after this we have to display the what? Output. So display the output as monitor as dollar symbol time, output Q is equal to D. So this is the format for displaying the output. That is a dollar monitor. So output Q is equal to D. So D means it's an decimal. So Q is equal to D, the command Q in the sense Q in the form of a decimal. So end the program, end module. So this is the simulation 1. Okay, we studied in laboratory. 0 nanoseconds, output is equal to 0. When it's 20 nanoseconds duration, Q is equal to 1. So it's 160 nanoseconds duration, Q is equal to 15. So after 160 it's continuation, 15, after 15 it becomes a 0 again. When it is reaches the 195 nanoseconds, then Q is equal to 0. So when finally, okay, here we have to write a $20 finish. So in the sense when it is come to 220, then output is equal to Q is equal to 2. Then after 220 it's stop the programming. So this is the what? A simple stimulus programming, we also called as a test bench programming.